Hello everyone, and welcome to our third and final PostLab of the unit, the area of a triangle PostLab, in which we will build a math model that relates the area, the base, and the height of a triangle. So this one's going to take a while, so buckle in. Right? Hopefully you've got your lab sheet out in front of you so that you can check your work as you go, and because you're going to need to add some notes when I show you how to take the two parts and put them together into one overall math model. So part one was area versus base with constant height. So in that case, we graphed the area in centimeters squared versus the base in centimeters, kept the height constant, and that resulted in a beautiful linear graph, right, that went through 0, 0, which means what's true of the relationship between the area and the base? Indeed, they are proportional to one another. So as you might have expected, a triangle with twice the base had twice the area. 3 times the base, 3 times the area. And you can probably see that in your numbers as well. We can, of course, create a beautiful... this is only true, though, if you keep the height constant. Important thing here, we're only doing part of the overall relationship. So if we use y equals mx plus b, right, our y variable is going to be the area, or capital A. That equals our slope. If we check out the slopes, again, these are the slopes from a few years ago. But if you look at them, you'll notice they are all very close to one another. In fact, very, very close to one another. It's a little easier to do estimations in this case than it was in the circle area lab. Notice we do get some 2.4s and some 2.5s. And then we get a few people who neglected to use sig figs, and so they just threw in 4 digits, because that's what graphical analysis told them. But in the end, we can round off to probably 2 sig figs would be appropriate, given that our measuring paper was 1 centimeter by 1 centimeter, so we can estimate to the nearest tenth. So we get an average of about 2.5. But notice, even to 3 sig figs, it's pretty much still 2.5, right? 2.49. So it looks like we got a pretty solid 2.5-ish here for a slope. So if we take that, go back, right, put that in. Units, well, how do you find a slope? Rise over run. So that is how we will find the units. The units of rise are area units, which are centimeters squared. The units of run are centimeters. Since this is a linear graph, I do want you to be able to tell me what that slope means, and I don't mean how much up and how much over it goes, right? But in terms of what it physically tells you about the area and the base. And I would like you, of course, to write it in a for every statement. So hopefully you wrote something like, for every 1 centimeter of base, you got an increase in the area of about 2.5 centimeters squared. For each additional 1 centimeter of base, the area increased by 2.5 centimeters squared. That's what the slope means here. The x variable is what we graphed on the horizontal axis, which is the base. Oh, sorry. Note that the units do reduce a bit. Right? The units do reduce. We get a centimeter on bottom, cancels out with 1 on top, and so we end up with 2.5 centimeters. Now, although this is important for us to know, as you're going to see when we get to the part where we put both parts together, in terms of interpreting the slope, it's kind of hard to do that, right, once you cancel the units out. So it is important to realize where the units come from to be able to identify what the slope means, even though that's going to kind of disappear here when we cancel out our units. Again, the x variable is the base. And then our y-intercept, well, you probably got a really small number, right? So something pretty darn close to 0. And statistically, it works out that way, but it also does logically, because a 0, 0 point on this graph would mean that when the base is 0 centimeters, right, the area should also be 0 centimeters squared. And of course, that makes logical sense. If you keep shrinking the base, right, you're shrinking the area down to 0 as well. And of course, you don't have to add a 0 y-intercept. So that becomes our specific math model, specific to part 1, in which we kept the height constant and hopefully you wrote down on your lab sheet that we happen to have a 5 centimeter constant height. 5 centimeter constant height and a slope of 2.5 centimeters. Wonder if those are related somehow. We shall see. So that's part 1 of the lab. Part 2 of the lab was area versus height with constant base. So when you graphed the area versus the height and kept the base constant, you again got a linear graph that went through 0, 0. Which means what's the relationship between the area and the height? Indeed, they are directly proportional. If you double one, you double the other. If you triple one, you triple the other. But in this case, remember, we had a constant base. So I have to talk about in a few minutes here how to put the two together. So again, we can create a y equals mx plus b math model out of this half of the lab. Our y variable is what we graphed on the vertical axis, which again is the area. And that equals the slope of these graphs. So again, if we gather them all up from a few years ago, you're going to see that they are all pretty darn close to one another. There's somebody who wrote 4 sig figs. Right? A couple of 2.9ers, even a 3.1. But the average to 2 sig figs is pretty much 3.0. By the way, these are all 3.0s that you're seeing here. Right? That's what they typed them in as, but the program rounds off. It doesn't like to put extraneous zeros unless I tell it to, right? Which I did down here. So to 2 sig figs, we get about 3.0. And notice again, it's pretty dead on 3.0, 2.99 even to an extra sig fig, which is more precise than our measuring device. So it looks like the slope of this one, we can pretty much assume is about a 3. So if we go in and put a 3.0, units, rise over run. Units of rise are centimeters squared. Units of run are centimeters. What does that mean? Well, it means for every 1 centimeter of height, you get an additional 3.0 centimeters squared of area. So this is telling you every slope is a rate of change. Every slope tells you how fast does one variable change when you change the other variable. When we add 1 centimeter to the height, we get 3.0 centimeters squared added to the area. So it's the rate of change of area with respect to changing heights. But again, the units actually cancel partially. The centimeter on the bottom cancels with 1 centimeter of the squareds on top, leaving us with a slope of 3.0 centimeters with reduced units. Again, it's hard to tell what that means unless you use the base units, right? But more conventional to reduce the units. The x variable is what we graph on the horizontal axis, or height. And the y-intercept, again, I hope is a really small number, because logically it makes sense that if our height is 0, our area will simply be 0. So this is negligible. You can neglect it. If you take 5% of your maximum area, it's going to be a much bigger number than your y-intercepts, than your little y-intercepts you got. And so, again, we don't have to add 0. So here is our specific math model for part 2 if we keep the height constant. And what was your constant height? Well, hopefully you wrote that down. And it was 6 centimeters, 6.0 centimeters. Constant base of 6.0 centimeters, a slope of 3.0 centimeters. Could those be related? Seeing a pattern? Well, let's go on. So what we've found thus far is 2 relationships. We know that when we keep the height constant, area is proportional to base. We also know that if we keep the base constant, area is proportional to height. But I would like to shove those 2 things together so we can see what happens when we have base and heights change. Well, we can do that. If area is proportional to base and area is proportional to height, my proposition here is that area is proportional to base times height. Now, you might have thought I was going to do some weird transitive property thing here with base and height. I wasn't, because that's the transitive property of equality. These are not equalities. These are proportionalities. There is no transitive property of proportionality. So there is no relationship between the base we chose and the height we chose. We could have done anything there with those, right? So then why did I multiply these together instead of add or subtract or even divide? Well, basically it's because that's the way it has to work in order to hold our original relationships and tell us what would happen if we change both. Let me show you what I mean. So let's say we don't change the base, but we double the height, right? We did that in part of the lab, right? We don't change the base and we double the height. We know that we should get twice the area. Well, that's what happens if we multiply, right? If we think of the base as being 1 because we don't change it and the height is doubling, 1 times 2 is 2. We get 2 times the area. That wouldn't work if we added them. 1 plus 2 is not 2, right? Or if we divided them, 1 divided by 2 is not 2. Right? So we have to multiply them. Likewise, if we doubled the base but kept the height constant, 2 times 1, we get twice the area. Kind of see what I'm saying here, right? So we have to multiply these two independent variables together in order to see what they do together to the area. Now this is more powerful because now we can change both. What if we doubled the base and doubled the height? Well, then 2 times 2, we'd end up with 4 times the area. If we doubled the base and tripled the height, we'd get 2 times 3, 6 times the area. See how that works? And yeah, again, this is something you got to be able to think your way through on a test or concept builders or those kinds of things. So now we can see what would happen no matter what we do to the base and to the height. We can see what effect that will have on the area. If we cut one in half and doubled the other, you'd get the same area back again. Yeah, it would look different, the triangle would look different, but it would have the same area. Again, this is why we multiply these together in these cases. So, this is better, because now we can change the base and the height and see what it does to the area, but it still isn't as powerful as it could be, right? Because we can't say this base, this height would be this area. To do that, we need to turn this proportionality into an equation. How do we do that? Well, we actually throw in another number out in front, which I'm going to call z. This is just a dummy variable. You can call it anything you want. You can make it a smiley face or a squiggle, all right? But this z is something which allows us to turn the proportionality into an equation. In mathematics, it has a special name. This is called a constant of proportionality. Here's the technical math definition. The constant value of a ratio of two proportional quantities x and y, usually written y equals kx, where k is the constant of proportionality. Isn't that clever? They use k for constant. All right. So this is the math definition. Basically, it's some coefficient you put out in front that turns it into a proportionality, or sorry, an equality, all right? Makes it an equal sign. So this is some extra number. Now, whether you know it or not, we've been doing that all along. I mean, think of our first lab. We had circumference proportional to diameter, right? If we throw in a pi, we get circumference equals pi times the diameter, and it turns it into an equality. So pi can be called the constant of proportionality between the circumference and the diameter of a circle. It's another mathematical way of defining what pi was. Pi also happened to be the constant of proportionality between the circumference, or the area, and the radius squared, right, of a circle. So if this is our constant, we don't know what it is. The question now is, what is it? What number do I throw in there, may or may not have units, that turns this into an equation? Well, thankfully, we have not one, not two, but 3 equations we've now created during this lab. Here's the one from our first half of the lab, where we kept the constant height at 5 centimeters and we got a slope of 2.5 centimeters. Here's the one from the second part of our lab, where we kept the base constant at 6 centimeters and our slope was 3.0 centimeters. And here is our general math model with our as yet unknown constant of proportionality, which I'm calling z. So can we figure out from looking at these what z has to be to make this general math model fit our two specific math models. Some of you might already be seeing it, but just in case you're not seeing what z has to be, I'm going to take this general math model and rewrite it to make it look more like the math model from the first half of our lab. And that's okay, because these are all multiplied together, and as you know, multiplication is both commutative and associative, so I can rearrange it and regroup it. So here's what I mean. I'm going to take this, and I'm going to rewrite it like this. Pretty okay with that? I just changed the order and grouped these together. Don't worry about the spacing. That's just to make it match up nicely. You see what I did there? Everybody okay with that algebra? Now compare these two. Here's our y variable, the area. Here's our x variable, the base. Here's our 0 y-intercepts in both cases. So for this general math model to actually be our specific math model, do you see where our slope that we got in the lab has to be z times the height? See my little analogy there? Right? If this math model we got from the linear graph of area versus base is going to actually describe our triangles, and our general math model, rewritten this way, is going to describe our triangles, then our slope had to be z times h. And since our height was 5 centimeters this entire time, what would z need to be? What would you need to multiply by 5 centimeters to get 2.5 centimeters? Yeah, z would have to be 1/2. If z is 1/2, 1/2 times 5 is 2.5. And notice that it doesn't need any units, because the height already has the units of centimeters, and the slope had reduced units of centimeters. So z can just be a number, kind of like pi was. You with me there? Well, let's see if that same thing works for the second half of our lab. Let me take the general math model and rearrange it. Again, I can do it because multiplication is commutative and associative. Well, we have the same y variable in these two equations, the area. We have the same x variable in these two equations, the height. We have the same y-intercepts, zeros. That means the slope we got in our lab must be z, our constant of proportionality, times the base. But in this half of the lab, our base was constant at 6.0 centimeters. So what does z need to be if our base is 6.0 centimeters to give us a slope of 3.0 centimeters? That's right, 1/2. And again, no units, because the base has the same units as the slope. I know that this is really mathy, and it's math you've never done before, right? But can you follow along here with what I'm saying? For our general math model to predict the two math models we got in the lab, z has to work out to be 1/2. This is actually how I set up the Google Forms. You know how in the Google Forms, if you put in the wrong slope, it tells you it's wrong? This is how I knew what the slope would be, right? I knew that if I drew you a bunch of triangles that had a base of 6, that our slope should be 3, because I knew what the constant was supposed to be beforehand, right? And that's actually the way it worked out. So, if we go back here and we say, all right, let's let our constant of proportionality be 1/2, and we plug that 1/2 in for z, we get the math model that your math teacher told you once in the past about the area of a triangle being 1/2 base times the height. So this was an experimental proof, if you will, of the equation for the area of a triangle, right? Based on its base and its height. Now, this is a long process, I know, because we had to take the two parts that we found and shove them together, and then we had to do some tricky little math to figure out what does the constant have to be to make everything work out, right? To make the first two parts of our lab predictable from our actual general math model. But in the end, if we do the math, we can come up with a math model that actually predicts nature. Now, remember, in math class, you probably did this by looking at, say, a square and saying, okay, if a full rectangle has an area base times height. Well, a triangle is just half of that, where one side of the triangle becomes the rectangle. Jeez, one half of the one side of the rectangle becomes the base of your triangle, right? And the other side of the rectangle becomes the height of your triangle, right? So they probably derived it theoretically, but now we can see that it actually works that way experimentally in nature. So I hoped you enjoyed this very long PostLab in which we determined the area of a triangle math model. 1/2 base times height.